Here is my model. It's a low-poly sardine with two maps, diffuse map and roughness map. GPU particles has by default a tool to distribute particles over the surface of a mesh, and this information is stored in position textures. If I want to create a different position texture, I can do it from this menu. I select the mesh and then the number of particles to distribute, or rather the number of spaces in the mesh surface. Here is the position texture. It is approximate, since by default Godot reduced the textures to a depth of 8 bits and not 32 as the original image. Basically, my idea was to make a very simple position distribution using a path and getting samples along it. Then save the positions in an ordered way in a position texture as Godot does on the polygons of a mesh. This texture requires a specific format called RGBF. I also kept an orientation vector on a second texture. Originally, GDScript returns a complete transformation, 3 base vectors plus a position vector. This information is too much to store in textures because then I will require 4 position textures. Instead, I just extract the Y vector and reconstruct the rotation matrix using this vector and the velocity vector. I also send other variables to the particle shader, such as the number of samples and also the segment size in order to determine the speed. In the script, I determine some input parameters such as the number of samples, the path to use, and the particles node. The size of the texture is constant because I think it's enough to handle a simple path. Now, all this code is kind of a cheat to avoid the structure of a plugin in Godot. It has some plugin features and requires defining a class name, all this in order to have a simple button in the editor. Here is the UI code to draw the button. And this function is the one that is executed when the button is pressed. As you can see, although I have used plugin classes, this is not shown in the options of the project, and is not required to activate it, so I will hide this code since it's only useful for the UI. Now, inside the function I have some checks for the path, the particles node, and the material shader. The variable step stores the size of the segment in meters. Then I create the textures with the RGBF format. There are several formats available, but this is the one that allows me to save the vectors in textures, since negative values are allowed. There is a version with alpha channel, but the RGBF format is enough. I create 2 images. Then I use 2 variables with the paged array format. Then the resize method to assign the size. Now I apply the path transformation to the points, because otherwise they are generated in the local space of the path. As I mentioned, I only extract the position vector and the U vector to generate a complete transformation inside the particle shader. Now, I assign the data to the texture, which are stored sequentially in the position texture. If I use the familiar setPixel method, then I will have to use a normalized vector for the color, but I need to pass a vector tree with no size limitations. Finally, I generate the textures and send all that information to the particle shader. I also send a completion message. And below I have this code that generates the textures as files, but it has complications. Now, let's see how the particle shader works with the information generated from GDScript. Here, I have the texture of positions, and with this, I obtain a series of points in 3D space. To improve the movement and to have less abrupt changes, I use interpolation between each positions. Now, let's imagine that this is the fish particle that is moving in space, with a velocity vector, and the little cross is the target. Although in itself the movement is already somewhat smooth, thanks to the interpolation, I am going to make a curved movement using steering forces, which is the velocity vector between the current velocity and the target velocity. If I assign a fraction of the force in each frame, I get a curved movement, for example, like this. So basically, I am using two ways to smooth the movement. I also felt the need to apply 3D noise to generate a more chaotic and natural motion. So this is the particle shader, and here is the include file that has the functions that I use. You can see that here is the noise function that uses this simplex noise function that I have already used in some shaders. Here I have created a group of uniforms called constants in the hope that the user realizes that he can change these parameters, because if he does, the whole shader is broken. It has some uniforms like path speed, random speed, noise frequency, noise scale, mass, radial speed. And here I'm getting a random value between negative and positive random speed, and I add it to the speed, then limit that value. Then I get the total distance by multiplying the seconds of time by the velocity in meters over seconds and get a random amount in meters. I also declare an initial position that doesn't depend on the random velocity. So if the random velocity is 0, the particles are distributed over the path on the z-axis anyway. Now this is the texture coordinate, and it's an integer because if you notice, here I am using the texture fetch function, which is different from the texture function, because it gets an integer position of the texture. In the t variable, I store a normalized value from 0 to 1, which is the remainder of the division between the distance and the size of the segment. Here, I simply wrap the value around the samples. This way, the index never exceeds the samples stored in the texture. Here, I get the next position. Now, I read the two positions from the texture and save them as vector, and now I make an interpolation between the positions using the remainder t. The polar random function gets polar coordinates from an integer. It does this by generating a random vector 2, and then those values are used to define the angle and then the radius of the polar coordinates by converting them to another random vector 2. Now, I need to convert those coordinates to the particle space using the transformation matrix. I apply the random diffusion to the interpolation, and finally I apply the noise. Here is my definition of the 3D noise function using the simplex function, as I had shown before. The function, clamp by max length, limits a vector using a float value, so I can limit the resulting steering force to the maximum velocity value defined in the uniforms. Now I apply the steering force dividing it by the mass. In that way, I obtain a curve and the coupled moment of the interpolation points. Finally, I have the interpolation of the cube vector that I extracted from the path transformation matrix. Again, I use the variable t. Now, I have to orthonormalize the basis vectors to form the matrix. In this drawing, I show the orientation vectors, which is basically the y vector. The problem is that with all the deformations that I make to the movement, as polar speed, steering forces, and noise, the resulting path can become completely different, having the same orientation vector. This could lead as a result that if I try to create a transformation matrix with these vectors, I will get deformations because the angle is not a right angle. What I require is an orthonormal matrix to apply to each of the particles, and at the beginning with this matrix, I was getting deformations like this in my fish particles. So in this line, I apply the orthonormalization to the y-axis. I got this from the Gram-Schmidt algorithm, which is this function that I was using, but I realized that I only need to apply the algorithm on the basis vector y, because I get the z vector by normalizing the velocity, and I get the x vector from the cross product, so it's already orthonormalized by default. And this is the final result obtained with all the features I mentioned before.